I'm Dr. Kieran Mulroney, and I'm actually one of the homegrown researchers here. So I started at the Perkins Institute in 2015 and actually did my PhD studies here. So I did that in the Translational Renal Research Group laboratory, and I'm a microbiologist by training. And so what I'm really interested in is looking at new ways that we can use new technology to get better outcomes for people with serious infections. And so, without further ado, I'll get into scaring you all to start with. Right? So, we go and we talk to people and they say, COVID was terrible. That was the worst thing that's ever happened. We want to look to future pandemics and we want to be prepared for the next one. What do we need to do? What is the next pandemic going to be? And the microbiologists in the room get a little bit awkward because the answer is it's already here. It's been going on for a long time. And what we're talking about is antibiotic-resistant infections. Infections that we don't have good antibiotics to be able to treat them at all, and it's antimicrobial resistance, the phenomenon that means that more and more bacteria and fungi are becoming resistant to these drugs, is what the pandemic is all about. And so, this is 2019 data that I'm going to be listing the numbers from, but there's already 1.5 million deaths every year just from the resistant infections alone. Now, if you think about that, we shut down the whole world for COVID for 900,000 deaths. And this is ongoing, and it's getting considerably worse because the 1.5 million is just direct mortality. So that is, you have an infection, you die in hospital because of it straight away. But if you look at the 3 months after a drug-resistant infection, that number goes up closer to 6 million people every year. Now that's scary to begin with, but in 2016, the UK government commissioned a report that was called the O'Neill Report, and it said, how bad is this going to get? And they said, well, we're going to see 250 million deaths before 2050. But they also said that we shouldn't get to 6 million associated deaths until 2041. And so we're overachieving, we're ahead of the curve, and in all the worst ways possible. And unfortunately, COVID is making that considerably worse. Going to remote healthcare and doctors having to give antibiotic prescriptions that they otherwise wouldn't have because they couldn't do things like put a stethoscope on someone's chest and say, actually your lungs sound clear, let's hold off, has meant that our antibiotic use has gone up almost 7-fold in the last 2 years in Australia alone. And that's not great. That is one of the major drivers of antimicrobial resistance, is antibiotics that you don't need to use, or using more broad spectrum antibiotics than you otherwise would. So when we're talking about the magnitude of that, we're talking about 1 death every 3 seconds worldwide. Kind of a scary number, but when it comes to talking about these things, a lot of times, some of the people in the halls of power only care about the dollar amounts and not the individuals. And so if you want to get those people to pay attention, we're talking about $3 trillion US lost in, GDP for people being unwell, being unable to work, loss of life, all of those things. So it is, an existential level threat that we're talking about. And right now we really don't have very good options when it comes to all of this. There are very few new antibiotics in the development pipeline, and the ones that we've got, we're losing them very quickly. And so, this is one of those big things that everyone sort of knows about, but no one really cares about that much. But there's this perception that, oh, that's happening somewhere else. That's not us. That's not anything else. And so this is out of Australian data. So this was published in July of 2022. It was the first review where they said, let's look at Australian hospitals and let's try to quantify just how bad it really is. And so what they went and looked at some of the 5 most resistant pathogens that we have in hospitals, the 5 worst of the worst. And so they found that in 2020 there were 1,000 resistance-related deaths in Australia. Not infection-related, just resistance on its own. And that's just from the top 5, right? And if you want to look at just how big the magnitude of that problem is, that is how much money it costs the Australian taxpayer every year just to deal with those resistant infections. And that's $438 million, right? It is big, it is real, and it's definitely happening in Australia. And so this is something that we really should be paying attention to, and we really should be caring about all of this. And so this is the basic underlying problem that we are facing at the moment. And so right now, many people who say you've got an infection, they say, okay, fine, I go to the GP, I get some antibiotics, and then I'm better or not in a couple of days. But that's not the sort of infections we're talking about right now. We're talking about really serious infections, the stuff that you go to the emergency department, you turn up, and it's life or death. And so right now, when we look at the pathology, if you want to be tested to figure out which antibiotic drug is going to work, they take a blood sample, they send it to the pathology service, then they'll try to grow a microorganism out of it. And that takes a day. And then once they've got that, they'll purify it, and that can take another day. And then they'll run the test, which unfortunately can take another day. And so now you're looking at sort of 2 to 5 days until you get actionable results that are going to help your doctor guide that treatment. And that's, you're either better or you're dead by that point. And that sounds really bleak, and that is the unfortunate truth of it all. And so, you know, we never want to show disrespect to the doctors, but at the end of the day, what they are doing here is they're making a best guess. Now, a lot of the time, that best guess is spot on. Everyone goes home, everyone is happy. But as resistance starts to increase, the assumptions that those doctors are making from their training and from best available evidence are becoming wrong more and more often. Those drugs that they rely on just don't work. And so what we need to do is we need to actually be able to change this. And this is, you know, where we came into this and said, we need to do better, we can do better. And so basically we came with this idea of same-day susceptibility results, right? You need to be, on that same day, providing guidance that says this drug will work if you use it, right? And so everyone knows, you know, if we can do rapid results, we'll have, you know, more certainty, we'll have better outcomes, and everyone, you know, applauds and says, yes, that's great. But how do we actually do that? And to do it, you have to understand what the problem we're really facing is. And so this is a graph that, you know, it looks a little bit terrifying and scary, and it's because it is. And so this along the bottom here is how many hours since you turn up in the emergency department saying, I don't feel good, my heart's racing, I'm sweating, you know, I'm feeling weak, something is wrong. And here, we're talking about your cumulative mortality risk, your percentage chance of dying, right? And so every hour that you don't have an effective antibiotic is a 6.7% risk of death. And that snowballs really quickly. And so here, we're talking at 36 hours, that risk of death is 100%. You will die. No ifs, no buts, no maybes. That's what's going to happen. And so if you talk to a doctor and you say, we're going to need you to wait an hour, they're not going to say yes. They can't, right? If it's a 6.7% risk of death, they have to just say, well, no, I'm going to give an antibiotic, and hopefully that's the right one. And so what we have in red out here is that's how long it takes to give existing test results. And that entire red box is at that 100% mark, right? And so what we really need to be doing is we need to be in this green box, because that's the green box of when that second dose of antibiotics is going to be ready, right? We're never getting in front of the first one. A doctor is never going to wait. But if we can get here, we can be in front of that second dose. And here, that mortality risk is still pretty low. It's not perfect, but it's better, right? And so that is the real scenario of what we need to be able to do. And that was the challenge that we took, and that's where we went with it all. And so I came from a background of doing really weird things with bacteria that you can't grow in traditional ways, and so using new techniques to measure them. And I said, well, if we don't want to wait for them to grow, there's some things I know about, we can try some stuff. And so I used a technique called flow cytometry, which this diagram looks terrible and scary and all of those things. But the simple part about it all is what we're doing is we're running a liquid suspension, like what comes out of a blood sample, through a capillary, and then using lasers to measure those cells as they come through. We're not going to wait for them to grow, but what we can do is say, let's make some measurements of all the individual bacteria in that. And we can do that really, really quickly. We can measure tens of thousands of cells every second using this technology. And so we can use all of these different, wavelengths of light and the lasers that, to collect so much information that allows us to say, well, okay, if we know what all of this looks like, we can measure the cells and we can say those are the human ones. We don't care about those, but we care about the bacteria in the blood. Now we've got a little bit of something because we can be measuring all of that sample in just a few minutes. So what do we do with all of this? And so we came up with what I call the flow cytometry assisted antimicrobial susceptibility test. And the reason it has such a long and cumbersome name is because the acronym for that is FAST. Makes it easy to tell people, right? And so we said, right, we need the pathology service to be able to do similar things to what they're already doing. And so what you can do is take that sample and you purify the bacteria that are in there. We don't wait for them to grow. We just say, well, there's lots of bacteria. We just need a few of them. Let's separate them from your blood. We then standardize it all out because people love a standard test. It's great for everything. And then we use a little robot that says, okay, let's just add that mixture of, the bacteria from the patient's blood sample to a tray containing all of the different antibiotics that a doctor is going to want to look at. And so we can do that. We throw it into an incubator for just a few hours because antibiotics only work when bacteria are trying to divide in the presence of the antibiotic. Right? And so you need to see that little bit of something just to be sure. And then we use our robot again. We add some extra, lab reagents to it all, and then it goes straight onto that flow cytometer. And we knew straight away, you've got to be able to do it so someone can press a button and walk away. We can't have highly trained scientists being responsible for all of this stuff. And so the whole process takes just a few hours to come back and to get us some results out of this. Great idea, but it takes a little bit more than that, just to go from an idea to something that works. And so hopefully these videos are going to play. So what we've got here is on the left-hand side, we have, it's just like a heat map. Each one of those dots is a single bacteria cell that we've measured. And the more red you are, the more cells are in that region, right? And so we're looking at something down here which is about the size of the cells. And this here is about how much DNA they contain and a few other parameters that are very interesting. But the one on the left is the one that's sensitive to the antibiotic. And so what I'm going to show you is as the concentration of antibiotic increases, you'll see what happens to the cells. And so immediately you see there's this huge change in that distribution. So we're saying thousands of those cells are all looking different, and they jump up straight up here to the right, which means they get bigger and they balloon out and they swell, which is what we know what happens to them, right? But then as the concentration of antibiotic gets higher, that population jumps back down. And if we put it under a microscope, we can say, well, that's where the cells are all shattering, right? The antibiotic is doing its job. And so you get this hook-shaped curve that appears through all of this, that you can say, well, that is how it looks if the bacteria is dying because of the drug. It's a pretty obvious stark pattern, and so we said, okay, that looks great, but what about a resistant one? Does it do the same thing, or is it actually going to be obviously different? And so we then said, okay, let's look at the resistant one. And so the concentration of drug is going up and up and up across all of this, and you can see that it's really not that fussed at all, right? It's just sitting there in that same region where we say, okay, they look fine. But then as we get to the higher concentrations of the drug, suddenly you see this start at the top here, right? And that is just a little bit of those bacteria dying. We still have that big population sitting there, the one that says, okay, these ones are going to resist it. But we're so sensitive and we're so specific now that we can actually say, well, some of them actually do die. And that's where some of those original tests can get confounded really quickly. Because microorganisms, they're not just, a static thing. They're not chemical. They are living organisms, and they're going to do whatever weird things they want to do. They're going to try to survive at all costs. And so we got to this point and we said, okay, it's kind of great. You can see them when they die, you can see them when you don't. We're at 3 hours now. This could be everything we need it to be. And so we went, okay, the lab is good, but what about the real world, right? You can't just assume that something that can happen in a science lab can go out there. And so this is that same graph that we saw before again, and this is the timeline. And so here, that's where the current stuff is. This is where we need to be. And so we went and we did a little pilot study, and we said we've got one scientist. That one scientist is going to work 9 to 5, Monday to Friday, and process samples for us, and we're going to run head-to-head with the pathology service over there and see how quickly we can get results back. And so here, this is the percentage of tests that is still remaining. So as you come down, that's good. And then across here, that is how long it has taken. So, this here, 24 hours, 1 day, 2, 3, 4. And so the red line is the pathology service, right? And so almost to get to half of the tests being complete, you're halfway through your second day at best. And they go all the way out to almost 96 hours to finish all of the tests. And so we get to 62% of all of our tests are done within 3 hours, exactly where we said they were going to be. And I show most people this graph and they say, why is it taking longer to do the rest of them? This shelf is samples that came in after hours and our scientist wasn't there to process them. And then these are the ones that he does on the second day. And then this is the weekend. It's when he's not there across the time. And so if you actually go through and you take out those, that line goes straight down. And all of those samples are done within 4 hours of having that sample. And so that it was encouraging. It got us to the point where we said, well, this could be something real. But we said, we know we can do better about all of this. And so we had our first major, preclinical trial of this technology. And we published that last year, and we put out some media about it. We were looking at patients who have indwelling surgical catheters in their abdomen to do dialysis. So, people whose kidneys have failed, they need this dialysis, but because we have to put that catheter in, the risk of infection is pretty terrifying for these people. And so they're very poorly served. We wanted to do better. And so we went and we did a real world, test of all of this. And so this darker red patch, that is actually the reality for those patients. This is where all of their, results actually came in. The earliest, I think, was 35.2 hours from off the top of my head. And it actually extends somewhere out into the corridor in terms of how long it took to get results back for people. But what we found is that we are right here in that window, so between 4 and 9 hours from the sample is where we actually came back. And so that's 148 patients, I believe, where we're really starting to achieve that same-day susceptibility answer. We're not getting in front of the first dose, but we will get there for the second one. And so, that was that study I'm talking about now. That was June 2022. And so we said, okay, I gave media interviews, I talked to members of the community, and the same question I got from everyone is, when can we use it? And unfortunately, the answer to that question is complicated, convoluted, and not often what people want to hear, because these tests are very, very highly regulated. They need to be, because we're taking literal life and death decisions off that. And so you need to do a lot of work between what works in a research lab and what you can get out there into the real world. And so I went away and I said, okay, clearly this is what the community wants, this is what they need, this is what we have to do next. How are we going to do that? And so one of the things that I immediately did was said, we've got to streamline all of this. It's got to be foolproof at the end of the day. And so one of the things I looked at was it's really hard to get just the data analysis side of all of this locked down. And so I partnered with a local firm called Three Springs Technology to then do an AI-based solution. Let's take the human out of it completely and let the computer make all of the decisions. And so we've been developing around all of that to be able to be better. WA government, we put the hard word on them and said, this is really good. It would help everyone in the community. Can you give us a bit of money to help drive this the next step further? And we were successful with that funding, which allowed us to purchase some new equipment to actually get a second site set up. So we've got some in the pathology service, but now we're also running a second research site out of this building here as well. And then we're moving on. So our next preclinical trial is aiming to report at the end of this year, which has got that evidence that we're going to need to take the next steps, to try to get this, regulated in Australia and overseas as well. We were able to bring a new team member on board, which is always, as a scientist, is gratifying, to be able to bring more scientists together and to get that critical mass of people working together. Buildings like this are great for it, but at the end of the day, that's where a lot of that funding that we're looking for goes, is supporting people. And Emily is an amazing young scientist, and I'm really proud to have her on the team. We're also looking at some of the weird stuff. Like, we're looking at now, instead of just bacterial infections, we're looking at fungi as well. A lot of people, they think about athlete's foot and a few others that are less pleasant that we perhaps skip over. One of the things that people don't realise is that if you go into the hospital and you look like you've got sepsis, a bloodstream infection, they don't know if it's a bacteria or a fungus, but they're not going to give you antifungals without solid evidence that it's a fungus, because they're extremely toxic to humans as well. And so even just being able to say, well, this is a fungus and you can use these antifungals has a lot of power. And so our study proving that it actually works for the fungi as well finished collection in March, which we're just about trying to get the evidence out there into the scientific literature. It looks amazing. Emily and Margaret, who's another member of our team, put in a lot of hard work on that one. I'm really proud of the work that they've done. But we got to May, and everyone starts asking, what's on the horizon. And the unfortunate part about these sort of tests is when you start talking to people nationally and internationally, people start talking about the money. How are we going to get it out there? How are we going to get the money? And the truth of the matter is, if you want to take a test like this from inception all the way to market, it's about $35 million. And that's not great, and it's not something that we can expect the community to bear the cost of along the way. And so that next big step has to be about, the commercial journey, impact and all of that. And so we can thankfully announce that we've been funded we got some money from the federal government to start up a new company called Cytophenics, which is a partnership with local folks. So the researchers here, some folks from UWA, Path West Laboratory Medicine, and the Three Springs Technology as well. And so we are now going to be taking that next big step. And as a scientist, I'm not really in my arena for a lot of this, but for me, it's all about that impact. It's great for us to stand in a building like this and discover new things, but if we don't get that out there into the community, for me, it doesn't feel right. It doesn't feel good. And so, if you want to do it and you want to do it well, this is the way that we do it. And I've actually just come back from the US, looking as to what that next step looks like and looking for potential partners to help us really accelerate what happens next. So with that, lots of people that we have to thank for the work that gets done. Perkins, University of Western Australia, Three Springs, Path West. But the government, Western Australia and the federal government have been very generous to us in support of the work we're doing. The Forrest Research Foundation kept me employed during COVID because it was a rough time for people with early career. The original pathway tends to be finish your PhD and then go to a prestigious postdoc overseas. And I submitted my PhD at the end of 2019, right as people were starting to rumble about this new virus that might be a problem. And so by the time I was ready to look at what happened next, the borders were closed and we were sort of stuck here. And the Forrest Foundation came on board with support for a lot of local folks. And immensely grateful. Charlie's, so the hospital here, they've been a big supporter of what we're doing. Lab Without Walls is a local not-for-profit focused on trying to get pathology services out into regional and remote Western Australia, the folks that are poorly served. And then Thermo Fisher Scientific, they're a big multinational that have been big fans of what we're doing and have helped support us along the way. Aaron, Margaret, Emily, and Tegan are the folks from the Perkins building, that's Translational Renal Research Group. And then Tim and Christine from UWA, and so this is our core team and the folks that have been driving along the way. So with that, I'll stop monologuing and we can go to questions for anything you'd like to know.